What if some of the most distant galaxies ever studied are not quite sparks at the edge of darkness, but bright cities forming sooner than expected? That is one of the big surprises from modern astronomy. When the James Webb Space Telescope began studying the deep universe, it found candidate galaxies from extremely early cosmic times. Some of them appeared brighter, more structured, or more massive than many astronomers expected for such a young universe. The key word is candidate. In astronomy, a faraway object is first identified by its light. Because the universe is expanding, ancient light gets stretched toward redder wavelengths during its long journey to us. Webb is built to see that faint infrared glow, but distance estimates can be tricky, so scientists use follow-up measurements, especially spectroscopy, to confirm what an object really is. What makes this fascinating is not that our picture of the universe suddenly collapsed. It did not. The Big Bang model is not being thrown away every time Webb finds an unusual galaxy. Instead, these discoveries are pressure tests. They ask better questions. How quickly did the first stars gather? How efficiently did early gas turn into stars? Did black holes help young galaxies shine more strongly than expected? The known part is powerful. Webb is revealing galaxies farther back in time, in greater detail than astronomers could study before. The uncertain part is how common these surprisingly bright early systems really are and exactly what makes them glow. Why does it matter? Because galaxies are the universe learning to build structure. Every star-planet, and eventually every world with chemistry, came from that early gathering of matter. The memorable takeaway is simple. The early universe was not an empty waiting room. It was already busy, already changing, and perhaps more creative than our models were ready for. And that is the first clue in a larger story. Astronomy often advances when faint light refuses to behave exactly as expected. Imagine learning what a planet's air is made of without ever visiting it, and without seeing its surface at all. That is the strange power of exoplanet atmosphere. Science. Most planets around other stars are too far away to appear as anything more than tiny changes in light. But when a planet passes in front of its star, a small fraction of starlight filters through the planet's atmosphere. Certain molecules absorb certain colors. To a telescope, the missing colors can become a chemical fingerprint. This method is called transit spectroscopy, but the idea is simpler than the name. It is like shining light through a mist and asking what the mist is made of. Space telescopes, including Webb, can search for signs of water vapor, carbon dioxide, methane haze, clouds, and other atmospheric ingredients on worlds far beyond the Sun. This does not mean scientists can point to a distant planet and declare it inhabited. A molecule is not a living creature. Even a promising combination of gases would need careful checking because planets can make surprising chemistry without biology. Stars can also complicate the signal. Star spots flares, clouds on the planet, and limited observing time can all blur the answer. Still, the discovery is enormous. For most of human history, planets were wanderers in our own sky. Now astronomers can begin to compare alien climates. Some are hot gas giants with inflated atmospheres. Some are smaller rocky worlds orbiting cool red stars. Some may have no thick air at all. What is known is that other planetary systems are common, varied and chemically readable in principle. What remains uncertain is which small worlds have stable atmospheres, liquid water, or conditions that could support life. The takeaway. We are not just finding planets anymore. We are learning how to read their weather from across interstellar space. And once astronomy can read air, the next question becomes even bigger. What hidden signals are still waiting in the dark? There is a kind of astronomy that listens for the universe, bending, not shining. For centuries, astronomy mostly meant collecting light. Visible light radio waves, infrared glow, X-rays, different forms of the same messenger. But the universe also sends signals through gravity itself. When extremely massive objects move in violent ways, they can send ripples through space-time. These ripples are called gravitational waves. The first direct detections came from stellar mass, black holes and neutron stars merging. Those events lasted only moments in the detectors, like sharp cosmic drumbeats. But astronomers are also searching for something deeper and slower. A low background hum that may come from many pairs of supermassive black holes orbiting each other across the universe. To search for that hum, scientists use pulsars. Pulsars are collapsed stars that spin and flash with astonishing regularity. Some are so steady that they act like cosmic clocks. If a long gravitational wave passes between Earth and those pulses, it can slightly shift when the pulses arrive. Not by much, but across many pulses over many years, a pattern can begin to appear. Several pulsar timing collaborations have reported evidence for this kind of gravitational wave background. The leading explanation is a population of supermassive black hole pairs slowly spiraling in the hearts of galaxies. But scientists are careful. The signal is still being studied, and its exact origin is not fully settled. Why does this matter? Because it opens a new sense for astronomy. Light can be blocked, scattered or delayed. Gravity waves carry information about motion, mass and collision in a different language. The known part is that the universe contains real gravitational wave signals. The uncertain part is how much of the slow background comes from black hole pairs, and whether anything more exotic contributes. The takeaway is quiet, but profound. Astronomy is no longer only about what the universe shows us. It is also about what the universe makes space itself. Whisper, from ancient light to alien air, to the trembling of space-time discovery begins with learning how to listen